All right, I think we're live. All right, thank you guys very much. So we have a pretty interesting talk here today, and I want to say thank you for everyone for turning up and joining this call. I think this is the finale in the Polkadot hackathon, the Builder Party hackathon, and this is one of the finale talks. So first of all, I'd like to say huge thank you for everyone joining, and congratulations, and well, good luck more than anything to all the competitors and the guys taking part in the hackathon. So I know it closes in a few days, so if you haven't checked it out, please do. I want to say a quick introduction for myself. My name is Remy. I'm part of the data team here, and I'm more than happy to be your host today. And we have a very special talk here today. And I'm going to hand the mic straight over to my colleague here, Andrei. He's going to do a quick introduction of who he is, what he does at Parity, and what he's got in store for us today. So, Andrei, why don't you take the mic?
Thank you, Remy. Hi, everyone, and thank you for joining my session. I have a very simple goal for today. Which is to convince you to build unstoppable applications on top of the Polkadot cloud. So I will demonstrate that Polkadot is ready to host scalable Web3 applications that feel as smooth as Web2. But first, I'd like to do a quick introduction of myself. So I'm Andrei, and I've been working at Parity for the past 4 years now. I'm a core developer, and I usually work on the low-level part of the Polkadot technology stack. So in these 4 years, I had the pleasure and opportunity to work on very interesting and challenging problems along with quite a few of the best people in the industry. My main focus, my main work is scalability and the user experience of unstoppable applications. Just a few highlights. So I worked on improving the network decentralization by increasing the number of validators, improving horizontal scalability by increasing the number of available Polkadot compute and bandwidth resources. And quite recently, I worked on elastic scaling, which improved vertical scalability for rollups. And this is actually quite a game changer. It really improved the user experience by enabling low latency use cases and allowing apps to scale easily in times of high demand. I will for sure talk about this a few slides later. Okay, so before we actually jump into the slides, I have to mention that I prepared a fun surprise close to the end of my talk. So it's a small incentive for you to stay tuned. So let's start. It's easy to understand why most people don't care enough about decentralization. Even in the industry, I looked at analysis which was showing that decentralization did not make it to the top criteria for choosing which platform to build on Web3 projects. That is quite unfortunate. And I ask myself sometimes, why would somebody even bother to go all the trouble with blockchains when all you need is just 3 MySQL database instances? I can tell you a few good reasons and examples why decentralization is super important. First, I'd like to highlight that most of the internet is now centralized. It's unfortunate. Applications, users, their data are actually owned by a few big companies. And it's unfair that most of the people feel in control when they actually aren't. Big tech uses people's data to their own and third parties' advantage. So I can give you some examples. Ads targeting. They have a large influence on what you buy. Social media is even worse. People call it the algorithm. You don't know how it works. It just delivers you content. It's totally under big tech control. The more you look at it, the more it locks you in. And it can get even worse. Recently, I actually read a report about how Meta was handling scam ad reports. In fact, they were doing nothing, despite the huge number of ad reports coming from users. Why? It's very simple, because that made them money. Scam ads. I would say this is evil. I'm quite optimistic about the future, and I'm excited to show you that you can build scalable and unstoppable applications that work and feel like Web2. This means Web3 apps are actually ready for mass adoption. And all of this is possible with zero compromises, decentralized, and censorship-resistant applications. So what actually makes applications unstoppable? I listed here are kind of the most important ones, call them pillars of unstoppable applications. What does it mean? It doesn't really mean zero trust. It actually means, I quote, less trust, more truth. But let me expand. It's all about proofs, proving something rather than blindly trusting. But the more you get practical about it, you realize that you have to trust the code, or you can check the code yourself. You need to trust math, you need to trust cryptography, you need to trust incentives, but never your users don't need to trust third parties, individuals, groups, authorities, or companies that have hidden interests. So that's an important property to have. Applications need to be resilient. That is required for redundancy. You need redundancy and global distribution, so there is no point of single failure. They need to be resilient in case of attacks done by malicious actors, hackers, governments, even companies. Call it competition. Many networks claim that they're decentralized, but most of them are not even sufficiently decentralized. So it's important that infrastructure is not owned by a single or few entities. Would your app be truly resilient if it runs in AWS and then an outage happens? Good, if I can say that, outages quite recently, like AWS and Microsoft. And actually, outages are a good metric to reason about how resilient a system really is. An unstoppable application is also censorship resistant. It's very important for its users. So myself as a user, I'd want that no one, no ISP, no app store or platform, not even the government, can silence my transactions, my posts, freeze my funds, or delete my account. I really like that. And the last one, no gatekeeper. What it means is basically about permission, more precisely less of it. The less the better. Permission to deploy and run your application and service for users. As a builder, you must be able to deploy any kind of application in a fully permissionless way. You don't have to ask someone to allow you to do it, like you do in AWS, for example. Why is it important? I think it's very important because, for example, let's say you built a really cool application, right? It has users, it has traction, but suddenly App Store or AWS decide they are changing the terms and conditions and they don't like your app anymore and just shut it down. The only gatekeeper for your app, the token holders, they voice their opinion and they make decisions through governance. So I want to recap. Apps are as unstoppable as the platform they're built on. The platform has to provide the correct primitives, which are resilient, censorship resistant, and permissionless. I want to make a small note here, especially for front end applications, because here mostly talking about the backend in a way. So even if the backend is unstoppable, your front end might not be. So please use light clients. Otherwise, you could accidentally depend on more centralized RPC nodes, like in infrastructure, that you make you fall short of being unstoppable. It took a while to get here, but I now believe we reached a point where all the work that went into building the infrastructure is starting to pay off. It is still very early, but we are already in the next chapter, switching focus from building the infrastructure of the Web3 cloud to building services and apps on top of it. The internet in Web3, if you'd like. So Polkadot is the first of its kind Web3 cloud. Is the most decentralized. It has the highest Nakamoto score of 178. I just checked it today. an order of magnitude higher than other platforms. The Nakamoto coefficient measures how decentralized a blockchain is by counting the minimum number of independent entities that are required to disrupt or take control of the network. Polkadot is super secure. All applications that run on Polkadot benefit from its shared security model, which is powered by proof of stake. And this means a lot for applications. It means composability. You can integrate other services or other apps that run in the Web3 cloud. Pretty much similar the way you do it in Web2, if you're familiar with that more. And lastly, it's super important, applications need to be sufficiently scalable for mass adoption. And this we will see how it happens in the following slides. The question is, can we call Polkadot a cloud or not? Right? So let's look at the definition. What is a cloud? Is the on-demand availability of resources, storage, networking, as services over the internet. It's basically made of many remote machines accessible over the internet. These machines store, manage data, and run applications. This is exactly what Polkadot is. Thousands of nodes running across the globe. We have validators, archive nodes, RPC nodes, sequencers. Clouds do it. Polkadot exposes a few key primitives that are the building blocks of applications or services. That it fits the definition. Let's see what are the differences and similarities between Web2 and Web3 cloud primitives. So in the left corner, we have the Web3 cloud primitives. And on the right corner, we have the Web2 cloud primitives. Let's look at the first one, the compute. So in Web2, which have physical CPUs, go for seconds of compute with serverless. Like, for example, AWS Lambda is a service. In Web3, we have a core time interface. And this allows you to go to the open market to buy and sell Polkadot cores. There are two flavors of core time. One is book. You get the core for a long period of time, like 28 days, for example. Think about it like Web2 VM reserved capacity, where you can go on demand. You can buy a single core available for your rollup for the next 6 seconds. Think about it like how spot instances work. And you can even think about serverless. I would say like contracts are very close to how serverless works in Web2. If you don't pay for the actual compute and storage, it's abstracted away, you pay for gas contracts. We can build a rollup and call it the Web3 VM, if you'd like. These are both good ways to consume Polkadot cores. Huge offering of storage in Web2. I just named a few things here, like AWS S3, like bucket storage, EBS, elastic block storage, and CDN, it's like for static content delivery. And in Web3, you have on-chain state and off-chain, like IPFS. IPFS is not a blockchain, it's just a distributed storage. Provides immutability, transparency, and decentralization, ensuring data is permanent or limited lifetime if required, publicly verifiable or privacy preserving if needed, and resistant to single points of failure. However, this comes with significant drawbacks, such as high costs due to every node storing the data. I may have some issues with my microphone, so Give me a second to solve it. Remove my headphones. Sorry for the interruption.
Still can't hear you, Andrei.
Okay, how about now? Can you hear me?
Perfect. There we go. We're back.
Okay.
Amazing. Sorry about that.
Okay. So I was talking about on-chain storage and how expensive it is. So given this difference, you'd want to be careful when you build apps about what you store on-chain. Do more with less on-chain. Push things off-chain. Really put large files off-chain. Just put a hash of the large file on-chain. That would make your application more scalable. Now, networking. In Web2, we have primitives like VPC subnets, just to name a few. These allow you to configure and connect your applications to other applications, the internet, and to interact with users. In Web3, it's very much similar, but it's different. There are different protocols. You cannot connect to the internet from Web3. You can connect to other Web3 networks if you want. So the primitives are HRMP, which is a transport protocol, allows rollups to connect and exchange messages in a trustless way with other applications running in the Web3 cloud. And then we have bridges. This allows apps to communicate with other blockchain networks, like, for example, Ethereum. It's something like the internet for Web3. Should have access to more than just what Polkadot Cloud has to offer in terms of services and apps. And you have XCM, which is a cross-consensus messaging format, which ensures your rollups can talk to each other. And it also works over bridges. So a small special note, if you're coming from Web2, Web3 primitives are more expensive and scarce. Do more with less, as I said, in terms of primitive usage in your upcoming Web3 apps. The on-chain storage and compute is for consensus. You should focus to put as less stuff as possible on chain. And now, lastly, we can say that Web3 clouds scale very much the same way like Web2. But there is a fundamental difference between Web2 and Web3 primitives. All of the Web3 primitives listed here on the left are resilient, censorship resistant, and permissionless. So you cannot build unstoppable applications on Web2. You can only build it in Web3. Now, since I mentioned scalability, let's talk a bit about it. So what is actually scalability? So basically, it's the ability of a system to handle increasing or decreasing workload efficiently by adding or removing additional computational resources. For Polkadot apps, it means adding and removing cores from your rollup or to your rollup. This ensures that users or usage can grow without performance degradation, maintaining app functionality and responsiveness as users' demands change. For Web3 systems, this is a challenging subject, and Polkadot is no exception. The more decentralized the system is, the harder it is to scale. You have many nodes across the globe, and you constantly have to deal with latencies, for example, 300 milliseconds, just because of geography, two nodes on opposite sides of the planet. It is important that scalability doesn't happen at the expense of resilience, trustlessness, or censorship resistance. After all, we want our apps to be both scalable and unstoppable. So to understand how rollups scale in Polkadot,
Let's take a deeper look at how the core primitive works. So Polkadot cores are different than regular physical CPUs. They're not physical, but logical. They're a fundamental building block, and they're atomic. You cannot split a core like a CPU. A CPU can split it. It has multiple cores, a physical machine, and you can assign them to different applications. This is not possible for a Polkadot core. You can have multiple applications running on a single core, but they have to be part of the same rollup. Okay, so how does the computation happen? Well, what's important about it is that it's impossible to predict which nodes will execute the computation. And this is very important for security. Which node does it is revealed as late as possible. Knowing this information ahead of time would enable malicious actors to prevent or alter the computation result. This would make your app pretty much stoppable or just insecure. So we want to prevent this. So for security reasons and censorship resistance, the computation needs to be done multiple times, but not too many, because the system would not scale then. The actual number of times it happens depends on a case-by-case situation, because the protocol cannot distinguish between denial of service or faulty nodes. We always assume the worst case just to be safe. There's also a minimum number of times it gets re-executed, which is around 30. That's for security. And we also have economic incentives baked in, so the bad guys stay away. They would basically get slashed and lose funds if they try to alter the outputs of some computation. So let's say you have got a core and you have assigned it to your rollup. Now, what can your rollup do with it? So your rollup can create a block that uses those 2 seconds of execution, does some useful computation, basically executing the user transactions. The block is then stored in the relay chain data availability layer, which can hold at most 10 megabytes in size for a core over 6 seconds. And then the relay chain validators will re-execute the computation and record the result on chain. Now, why every 6 seconds, you might ask? So this is because Polkadot is also a blockchain, and blockchains measure time in blocks. And in our case, the relay chain clock ticks every 6 seconds. A block is built every 6 seconds on the relay chain. And every 6 seconds, and with every block, all of the cores of Polkadot are allowed to do work for at most 2 seconds. The rest of the 4 seconds is required for consensus. Now, if you're curious why does a Polkadot core need bandwidth, the answer is very simple. For the same reason why physical CPU is needed. A physical CPU has a memory bus that connects it to the system memory. The Polkadot DA acts like system memory, and the internet is the memory bus. It has the same purpose as in a physical machine, to make the input data available to the CPU. As you can see in this chart here, Polkadot is leading from far away in terms of how much bandwidth it can provide to all of its 100 cores that are currently available. But however, as you'd expect, the data availability layer has properties like trustlessness, permissionless, and is decentralized. Since it's not known ahead of time where the computation will take place, the DA makes no assumption. It would be easy if you make an assumption. Having the data already there near the physical compute, it would make things much faster. But at the same time, you say goodbye to security and censorship resistance. So for this reason, we use erasure coding, which gives us redundancy, and all validator nodes store chunks of the original data. Anyone, not just the validators, can recover the original data with just 1/3 of the chunks. This allows us to have and tolerate 1/3 of nodes being actually malicious and returning invalid chunks, trying to prevent you from running the computation as a validator. So now that we talked a little bit about how the core works and what it offers, let's see how scaling vertically works in the Web3 cloud. So from a bird's eye view, rollups scale vertically pretty much the same way a VM does. You add more CPUs, cores to handle the extra load. But if we look deeper, a rollup uses the cores differently than regular VMs. A rollup still needs to produce a chain of blocks. There are not 2 chains or 3 chains, just one. The more cores the rollup has, the faster it's able to produce blocks. This has some benefits that are important to the user experience, like ability to run the application at scale through vertical scalability, lowering the block time, increasing the maximum available bandwidth for the computation, and increasing the maximum TPS. So yes, Polkadot cores can be used by apps in different ways. You can even have a core once every 60 seconds or once every hour. But most importantly, Polkadot apps can use multiple cores. And you have elasticity. You can dynamically change the amount of cores that you use. And this requires no code changes, like very simple changes, just a few constants. It's very easy to maintain, and it has this like great benefit of improving the user experience along with TPS. So for example, let's consider that you built a rollup hosting an application, and with a single core, it is able to sustain around 1K TPS. Well, we know that transactions are not created equally. The amount of TPS you can do depends on what transaction actually do. So in this particular example on the slide here, the workload is CPU bound, meaning that the bottleneck is those 2 seconds that a core gives you. So fully using one core gives us 1K TPS, meaning that each block will contain 6K transactions. That amounts to 1K TPS. So if you scale up by adding 2 additional cores, you will triple the throughput, so your rollup could do 3 times more. And not just that, at the same time, because it builds blocks faster, at a faster rate, you'd get this nice 2-second block time and more data availability. But if we give it 12 cores, the TPS remains the same. The block time goes down to 500 milliseconds because it builds 12 blocks every 6 seconds and get more data availability. But why the TPS doesn't increase? So this has to do with the fact that we don't, like the rollup doesn't do parallel computation. At the rollup level, everything is sequential. You build a chain of blocks. But if the workload was bounded by the DA bandwidth, let's say it had like transactions which contain big blobs of data, then actually adding more than 3 cores would have improved TPS up to the point where either CPU or again, DA becomes a bottleneck again. So it can happen that scaling vertically is not sufficient. If that happens to your application, this is a good problem to have. You have probably found product market fit. It's not easy to solve, but it's doable. What you need to do, you go multi-chain. You split your application state into interoperable shards. This will introduce additional complexity and challenges, like requiring asynchronous communication between the shards, so that you'll have to do significant logic and code changes probably. Like you have to figure out how you shard the state of your initial rollup so that you minimize the amount of cross-shard communication that needs to happen. Because additional latency for cross-shard operations is a challenge. You'd want to minimize that. So how can Polkadot deliver a Web2-like experience for Web3 apps? So this basically is done by providing some solutions for a couple of common Web3 user experience problems in terms of latency. So block time is actually quite impactful to the user experience, depending on the use case. And we know that fast blocks can significantly improve the experience if the app can make decisions based on a transaction being in a block and observing its side effects. For example, buying a coffee. You don't want to wait for finality for 30 to 6 seconds. You'd want to get your coffee as soon as you see payment in a block. However, if you're buying a Lambo, you probably want to wait for finality and for that transaction to be, settled. So, the seller gets the money, you get the Lambo. And then Polkadot solves it by allowing you to have these fast blocks and transaction confidence, meaning that you can see the transaction in a block and have some soft guarantees that it will be finalized. And there's another thing that you can do if you want to improve it even further. There's a playbook of things like progressive feedback, optimistic UI, basically simulating what will happen when a transaction gets actually in the block. Or you might want to bundle or batch multiple user interactions in a single signature, so the user doesn't have to go all the time and sign and wait for multiple blocks for a simple action to happen. Now, let's say your app works smoothly, but you have this other problem of TPS spikes. So the usage of apps is usually not constant. You have, depending on the app and the user base, you have spikes. For example, spikes in the weekend, in the evening, when people get back from work, Black Fridays, right? So spikes can break your nice responsiveness of the UI by forcing users to wait for minutes. This would basically raise costs, and it will kill user retention. Polkadot can fix it. You can scale vertically by adding more resources, and if that's not enough, you can shard. And at the whole Polkadot level, you can get pretty high with the multi-chain setup in terms of how many transactions you can handle during these TPS spikes. And the last problem that is solved by Polkadot is the data bottleneck. As we seen in the chart earlier, there's a lot of bandwidth that's available for computation. So even if you have a fast compute, if you're not able to bring the data in, it doesn't do anything. So if your data availability is slow, your user still waits for a transaction to get in. So in Polkadot, this can again be easily fixed. Like all of this, it can be fixed by scaling vertically your rollup. So you can do 1.6 megabytes of availability per core, with just single core, and up to 20 megabytes with 12 cores. So this can satisfy a large number of use cases. So what kind of apps can be built on Polkadot? Any kind of application. Whatever you build, if it's built right, it's unstoppable. You can choose either to build as a rollup or use contracts. Both have advantages and disadvantages. The way I see it, the guidelines should be that you start small with contracts on Asset Hub. It's cheap to start, it's cheap to iterate, it's easy to build POCs, and you don't need to run any infrastructure as it is already provided by the Asset Hub rollup. Once your app has traction, there might be benefits in switching to a rollup for maximum performance or flexibility or bigger scale. Running rollups is way more complicated than using contracts and is more expensive in terms of deployment. You need to run sequencers, RPCs, and archive nodes. But no matter what you choose, contracts or rollups, Polkadot offers support for high TPS, low latency, and high bandwidth applications. You can even pick all three of them. So with all of that being said, I'd like to challenge you to think deep. Think about the motivation behind unstoppable applications. What you build doesn't have to be something fancy, but it has to be something that can only exist in Web3. That gives it real value. Solve a real-world problem for groups of people. Find a solution that brings freedom to some people who are not even able to enjoy the illusion of being in control of their life. Now, as I promised you earlier, have some fun on the agenda, and I will like you to join me in playing a little game, if you'd like. It's a Web3 game. It's actually a very simple and classic game I developed especially for this session, Very simple example. But it should demonstrate that Web3 apps can work and feel like Web2 in terms of latency. So let's play a fully on-chain game. So we'll be leveraging 12 cores with 500 millisecond fast blocks. All of the game logic and storage is on-chain. So are you ready? Please scan the QR code or just enter the URL. I think it's best that you go for the desktop. It also works on mobile, but I haven't spent much time to make it smooth there. Okay, I'll give you a couple of moments to onboard. Copy the link, scan the QR code.
Do we want to share the game on the screen, Andrei?
Yes, I will do that. If possible, can somebody paste the link to the audience? Maybe that makes it easier.
Yeah, of course I can do that.
Thank you, Remy. And once the UI loads, it's very easy to get started. Click Create Account, enter something, a unique string, because it will be used to derive some keys for you, and you don't want that two people entering 1, 2, 4, 3, 1, 3, 4 will get the same account. Share an account. Then click Start Game and wait for the matchmaking system to pair you with a playmate. And I'll do the same. I will also join the game. Let's see if I win. Okay, so we can see here the stream of blocks is like those fast 500 millisecond blocks. The transaction history and transaction timing analysis. Like what kind of, you can see like these stats actually impact how you feel the game is running for you. So let's click Start Game. And let's play.
So this whole thing is entirely on-chain then?
Yes.
That's incredible.
It's fully on-chain.
Are those, do you say 500 millisecond blocks?
Yeah, I can see them up here.
Those are the famous Basti blocks.
They're not the Basti blocks. This is like by using 12 cores.
The
I would have blocks that actually have the full support. Like it's coming up for sure. Okay, I didn't win. I'll try another round. Just get back to the matchmaking. Okay, I think that there's a glitch here. Still says it's a draw, but it's not.
But it seems to me this is sort of like the start of, something huge. If this can be done entirely on chain with this such low, very little latency, could you build like even more complicated and complex games on top of this?
Yeah, you could, but like I said before, like the resources are quite scarce and expensive. So ideally, you'd want to put as less stuff as possible on chain. So putting less stuff on chain and doing, let's say, the heavy computation off chain is the way to go. Your app can scale much better if you do that.
Makes sense.
Well, on chain is for consensus. So like for important logic, important decisions should happen on chain. And
sounds good.
provide proof from off chain about what happened.
So we're a little way from getting GDA 6 on chain just yet.
Okay, so I mean, people can continue to try it even after the session, and I see that we have 5 more minutes from the allocated time. So thank you all for playing my game. Really appreciate it. And I like to hear some feedback. But more than that, I'd like to hear some questions from you.
Okay, if you guys have any questions, this is probably the time to post them. So feel free to comment in the YouTube or the X, and we should be able to get them here. We have one question, which is actually going back to what you talked about previously regarding rollups not doing parallel block building. And how could you maybe go back and just reiterate on how rollups make use of these extra cores?
Okay, that's a good question. It is a bit counterintuitive because, like in Web2 systems, like in regular VMs, you have more cores, then you make your app multi-core and it just runs computations in parallel. Here, we cannot actually do that because we have to build a chain and we have to build it block by block. So we're in a sense a bit limited in terms of how far you can scale vertically because of the sequential nature of the application logic. So the runtime, for example, is single threaded. It doesn't support multiple threads. At the same time, we don't support building multiple blocks at the same time. Maybe in the future, we might figure out some better solutions here. But at the Polkadot relay chain level, you have parallelism. So cores do computations independently from one another. They don't require the outputs from some other core, the plain text outputs. They can just like, they're happy with just hashes of the output of some other computation.
Makes sense. Okay, amazing. Thank you. We have one more maybe. So why is the trustless decentralized verification important, specifically talking about the computation here?
Okay, so this is where the security comes from. So we have these protocols, it's called else, where once you have a block that is stored in the DA, you have this process of checking if it's correct or not. So here, we actually don't want that it is known ahead of time which validator will check what. Because then you could have malicious actors that would benefit from this information and wait for the right time and even DOS other validators, so they're not able to do the computation. So only malicious nodes perform the computation and give a wrong output. Like they, instead of having certain transactions in that block, they could just replace them with other transactions, and basically breaking the security of the application. At the same time, it could censor them. So like basically censoring the execution of the parachain blocks would basically stop finalizing, would stop the finality process for that specific parachain block. So we don't want that to happen. So it's important that we have this like trustless properties for these protocols. They need to be censorship resistant, and we kind of go to great extents to do that. Like we waste a lot of bandwidth and CPU by re-executing. So whenever we see that a node has not sent its like outputs from its execution, like approving that a certain execution is correct, we'll assume that it was taken down, censored from doing so. So we have this escalation protocol. So instead of just one, two or more validators will start checking that rollup block, and it can go all the way until all of them do the check, if needed, just to ensure security.
Perfect, amazing. Thank you so much. I think we are at the end of the stream now. So I think maybe just one more question for myself. Andrei, I'm guessing all of this will be made available in public at the end of the call. So if any of the audience members want to read through these slides or check out the game again, this should be all publicly available afterwards, and we'll definitely post some links to this after. But I think we're going to have to close this out now, because you just hit the 45-minute mark. So I want to say a huge thank you for everyone tuning in today, and best of luck to everyone taking part and competing in the Polkadot Builder Party Hackathon. So I'm really looking forward to seeing some of your projects. And again, thank you so much, Andrei, for joining us today. That was really, really interesting, and I really love the game. I think it's a stepping stone into something huge, and it's just a demonstration of what can really be done. So if there's any builders out there who want to build something really cool, anything at all, please join. Please come have a look. Polkadot is always looking for more builders, and get involved. I think we're going to have to cut it there. But again, once again, thank you very much. And I'll see you guys next time.
Thank you.
Thank you.